All right, so let's go ahead and get started with the Unit 2 for the Algebra 2 Semester A, Unit 2, but factors, zeros, and solutions of polynomial equations. So again, we're kind of revolving around the idea of polynomial equations. We've we've had we had a tutorial that was focused solely on factoring. Now we're going to apply how we use the factoring to relate to the zeros. So kind of like in the previous tutorial, you learned about roots and solutions, how they kind of wrapped those two words in the same idea with zeros. It's if I ask for x-intercept, zeros, roots, or solutions, you're pretty much asking for the same thing. It's just that we name it differently. Kind of like in math, like if in order to take the average, you also can take the mean. Um, so though it's kind of like we're using multiple different names for it, but it all represents the same thing. So how are we going to relate factors to zeros? Well, the first thing we're going to go ahead and do is get a little refresher of the factors on our warm up here on slide 5. So I'm going to go ahead and walk a couple of them with you, and then you can go ahead and do some. But some of them should look familiar, like this one. Go back and take a look at your notes for the difference of squares. This one, we're going to go ahead and take a look together. This one has 4 terms, so you can go ahead and do grouping. And the last one, you can do a GCF, which we'll do the 2 middle ones together, and then I'll let you to go ahead and do the first and the very last one. So the second one, right? It is x to the third power minus x squared plus 3x minus 3. Because I have 4 terms, what I want to do is go ahead and I want to group the first 2 terms and group the last 2 terms, and I have it split with that plus sign there. And the idea is that within the first set of parentheses, what can I factor out from both? So by taking a look at it, x cubed minus x squared, I can factor out at most an x squared. And here, by this one originally had 3, now it goes down to 1 minus. Now, if I took out just the whole x squared, you're going to represent that by 1. Then we have our plus sign. Now we take a look at the second set of parentheses and see what we can factor out from there. And they don't have a common variable to take out from both terms, but they do they both have 3's. So we can factor out a 3, or in other words, they're divisible by 3. So then I have x minus, keep the same sign, 3. If I took it out, I'm just going to represent that as a 1. So then we continue moving on to that step. And if you notice that you have a parentheses with x minus 1 and another parentheses with x minus 1, so you can go ahead and factor that out as well. So then let's factor it out, x minus 1. If I remove this, what are we left with? You see x squared plus 3. So that will be in its own parentheses as well. X squared plus 3. And you can kind of see it matches up to this one right here. Now, in the last tutorial, when we were dealing with complex numbers, we're actually able to factor this even more, but now we're actually stepping away from the imaginary world and we're just trying to factor out as much as possible, but for real solutions. Now, let's go ahead and take a look at the next one, which is 2x cubed. 2x cubed plus 2x squared minus 12x. So this one's going to use a combination of GCF and also the giant x. And again, you're going to, for the very last one, x squared minus 6x plus 8, you'll do the giant x. X squared minus 36, you'll see that if you resort to the last one, but that one is the difference of squares. So again, make sure you double check on those notes from when we were factoring polynomials, those different types of factoring. So for this one, I analyze each term and I know that they're all divisible by 2 and they all have an x. So I'm going to factor out a 2x. So by factoring out a 2x, I'm going to put them in parentheses and write out the leftovers. So by 2x cubed divided by 2x is just now x squared plus 2x squared divided by 2x is now just x, minus 12x divided by 2x is negative 6. So that 2x is already factored. Focus inside the parentheses. Can I break it down anymore? I have 3 terms. It's a giveaway to do the giant X. Now remember the giant X, you take because it's already in standard form, you take your A value, and this is again very familiar when you are identifying A, B, and C for the quadratic formula. You take your A and multiply with your C to put it at the top. So your A is 1, your C is negative 6. 1 times negative 6 is negative 6. The bottom is your B. So your B right here, we have 1. So now remember, they need 2 numbers that go right here that multiply to get negative 6 and add to get 1. So the multiples for 6 is 1 and 6, 2 and 3. Which pair can give me 1 if I try to add or subtract? 1 and 6 can either give me 5 or 7. That doesn't work. 2 and 3 can either give me 5 or 1. And the reason I do that is just by adding them and then taking the difference of them. So the difference of 2 and 3 is 1. So if I put 2 here and 3. Now, one of them has to carry the negative, so I'm just going to try it out with my 2 first. Negative 2 times 3 is negative 6. Negative 2 plus 3 is positive 1. So we were able to break the parentheses in here. 2x is still holding out on the outside. We have parentheses x minus 2 and then x plus 3. So don't forget, again, when I'm writing out these examples, you should be following along and writing them out yourself to get that practice. Don't forget that you can go ahead and pause the video and stop it, work on it, and then come back to it because I will be continuing on. So this one, even though it's in a different order, it still represents the same factorization. So this one is completely factored for 2x, x minus 2, x plus 3. So then you're going to go ahead and do the other 2, or if you are still a little bit uncomfortable factoring it out, you can go ahead and multiply them using the FOIL method or distribution method, or like what I like to call it, banana method, to match up to your answers there. Don't forget to simplify. Moving on to slide 6. So it says, let's take a look at the quadratic equation that's graphed on here on the right-hand side, x squared minus x minus 6. In this equation, the function is equal to a factorable polynomial. So what they did for us is they factored x squared minus x minus 6. They factor that polynomial to get x minus 3, x minus 3, x plus 2. And that equation is actually coming from our warm-up. Now, they're saying that if you have the factors, you can determine the zeros. What does that really mean? Well, remember what I said, zeros, solutions, and x-intercepts are all the same thing. So as they have it right here, the red dots, they have x equals negative 2 here, and x equals 3. So the solutions are negative 2 and 3, or you can do it algebraically by factoring it. Now, here you do have to take an extra step. You have to make sure that this was set equal to 0, and then separate the 2 factors. So you would have x minus 3 is equal to 0, and x plus 2 is equal to 0. And then you're asked to solve by getting x alone. So this minus 3, opposite of that is adding 3 to both sides, which we get x equals positive 3. And then this x plus 2, we subtract 2 on both sides, and we get x equals negative 2. Our answers match up to our graph. Now, again, what happens if you're not always given the graph? You can graph it yourself, but the idea is where I want to give you the zeros, and you generate an equation for me from that, or vice versa. The idea here is that we're looking at specifically at a quadratic. What happens if I deal with a polynomial of the degree of 5? So that concept of whatever the highest degree is how many solutions or zeros I have to that polynomial. So this is x squared, tells me that I should have two answers. Nope, -2, +3. So like, do you see that connection there though? So here's another thing if you haven't noticed already. Here I had originally x minus 3. My final answer is x is equal to +3. So do you see, once we have the factors, I can pretty much skip a step and jump into like, oh, x is equal to 3. And then here, because I have an x plus 2, my final answer is going to be x equals to -2. So it's just something to point out to make your lives a little bit more easier when it comes to that. But again, you need to write out your steps. Go ahead and do so. Let's go ahead and take a look at slide 7. So polynomials in factored form. So we're going to look at strictly factored form. So the idea here, and you know what, if you don't mind, I'm going to go ahead and kind of give you, like, again, an example of what we're going to be seeing. Instead of this saying A, B, and C, let's just say that this is -3, this is +1, and this is 2. So if I tell you my zeros, right, because there are going to be some examples like that, my zeros are -3, +1, and +2, how would I write this in factored form to form my polynomial? So I do the opposite sign of it. So I have a -3 here. I should have an x plus 3. If I have a +1 here, this is going to be x minus 1. So do you see, we take the opposite sign, but we're working backwards. Here I have a +2. This is going to be x minus 2. So we have those set up. And then here, if you were to multiply this out, we would get x cubed. This graph is a cubic function. So keep in mind that, see that connection between them, because then that's going to be super helpful within the next couple of slides. So let's take a look at slide 9. So here it says, let's consider a polynomial with zeros -1, 1, 4, and 6. So we have 4 zeros, and they actually have them listed for you on the graph. So it says the polynomial must have a factor of x plus 1. So again, what if we write these out? It's -1, 1, 4, and 6. So each zero that they give us, or each x-intercept they give us, we know a factor. This is going to be for x plus 1. Again, do you see that sign change? Same number, is just a sign change. Here it's +1. Now we're going to have x minus 1. +4 is now x minus 4. And this +6 is now an x minus 6. Again, if you put these all together, we don't know the actual shape of the polynomial, but if you were to multiply them all out, you should get the same intercepts. And here is our polynomial. So it is a degree power of 4 because it touches the x-axis 4 times. And again, those are your solutions every single time it intercepts. So they remove the x-intercepts, but again, here though, they did give us the function, the complete function. This is just a rough estimate, it's not a rough estimate. It is a part of the polynomial. The thing is, it has this a value sitting in front. So if I were to like squish them in together, I can say that this is y equals a parentheses x plus 1, x minus 1, parentheses x minus 4, parentheses x minus 6. So right here, how would they determine this a? I would need to know another piece of information about this graph, like a y-intercept or another point, to plug this information to solve for a. Here they did give it to us. G of x is 3, or it's 3x plus 1, x minus 1, x minus 4, x minus 6. So they actually gave us that value. But again, in some cases, we might just be given a point, and we plug it in to the x's, right? Because a point is x comma y. So we'll plug it into the x's and to the y. And you see the only variable you don't have is a. So you should be able to plug it in, solve for your a, and then plug it into this general equation that we still have here at the top and remove the a for the actual number that it represents. Oops, that's supposed to be a y. Sorry about that. Okay, so let's go ahead and move on to slide 10, which is going to be, it's going to be a question very similar to what we did. So here they're going to give you a list of the zeros. You have to come up with their factors. So this is just a general thing. Again, remember you're going to take opposite signs. So here we have them in order, right? So it is -5, -1, and 7. All you got to do is come up with the factor. Remember, opposite signs. So if I do one of them, for -5, you should have x plus 5. Go ahead and follow the same rule for these and type it down below. So you have 3 sets of parentheses for your 3 zeros there. Moving on to slide 11. So factored form for a graph. Again, here they generalized it with A, B, C, and D. Again, that same idea that you're going to take, that you might be given the zeros, you just plug it into the factored form of it, or go from factored form into those zeros. So it's kind of like following the sign and taking the opposite of it. The numbers are still the same. So it says, consider the graph of a cubic function. The graph crosses the x-axis at points -3, 0, 0, and 2, 0. So they give me the graph and they tell me the zeros. So the x-intercepts, right? It's going to be -3, 0, and a 2. And if you follow it here, there's -3, there's your 0, and there's your 2. How do I come up with the factors there? So again, I set up my parentheses. Now 0 is an interesting thing, but let me do -3 first. We should have x plus 3. To represent x, or to represent 0, it's just an x. Then for 2, again, opposite sign, -2. So if you put these factors together, I like the x not to be in the middle. I'm just, because it looks kind of like saying, oh, multiply x plus 3 and x minus 2 when it's not the case. Just bring the x to the front. So then you have x plus 3 and x minus 2. Again, you're just working backwards from the information they give you. Here, so let me kind of clean this up so that we can go ahead and state what they're stating, or look at what they're saying. So because the x-intercepts represents the zeros of the function. So remember, x-intercepts, zeros, roots, solutions, they all represent the same thing. We know that they have the zeros at -3, 0, and 2. So we got that info. Rewrite the zeros as x plus 3, x and x minus 2, exactly what we did. And that's the equation of it. So I forgot to finish off this equation as y equals x, x plus 3, x minus 2. So when we have a 0, that the number 0, right? It's just going to be x. And then we like to move it all the way to the front of the polynomial because it just looks nicer. It doesn't have, technically it's like the idea is that it's like you have 0, you're doing like x plus 0 or x minus 0. But it's like, what's the point of writing 0? That's why we just write x. Moving on to slide 13. So we're going to go ahead and match the tiles here. So by looking at the graph, make sure you list out all your x-intercepts. So for this one right here, for the first graph, you have it touching at -4. So we'll write it out here, -4. And that is at +1 and +4. So 1 and 4. So right there, you have 3 zeros. You should have 3 factors. So go ahead and generate the factors for each of those zeros there and match it up. Does it have to be in the exact order as yours? No, as long as you have each factor for every one, you're set. Now double check and do the second one, repeat the same steps. Find out where it touches on the x-axis, write out those numbers, and then do the factors for each one. And that will be it for slide 13. So solutions of the polynomial. So remember, zeros, right, are the solutions to these polynomials. It's again, it's all within the same context that we're talking about. So now we're going to go ahead and discuss it. So the idea is that we're kind of like making that connection, like going from factored to finding those zeros, or using those zeros to go into factored. It represents when you're going from factored to get the zeros, those are the solutions to the polynomials. We're skipping a step in between of what's actually going on there. And that step that we're kind of skipping, or that I did bring up, but we're kind of skipping at some point, is the zero product property. Okay, so if A times B is equal to 0, then A is equal to 0, or B is equal to 0, or both. So this concept of zero product property is we are going to be multiplying, right? But our A and B is not just a number A or B, right? Because it doesn't matter, right? If it's A is A times 0, right? Saying if, oops, let me go backwards. So it's A times B is equal to 0. What if A is 0 and we multiply that with B, we still get 0, right? Or if it's B that's equal to 0, do you see we still get 0? But what if they're both equal to 0? Still 0. So that this concept is also related to our factors. What if we said x plus 3 and x minus 1 is equal to 0? This whole factor is your A, this factor is your B, right? So here, if we take the zeros from there, which this is -3 and +1, if I plug in if x is equal to -3, you get -3 plus 3, -3 minus 1. Is that going to equal to 0? Is this zero product property true? So -3 plus 3 is 0 times -3 minus 1, -4. 0 times -4 is still 0. It works. Checks out. What about 1? So right here, we replace x with 1. 1 plus 3, 1 minus 1 is that equal to 0? 1 minus 1 is 0. Oops, 0. 1 plus 3 is 4. 4 times 0, still 0. So this is the idea. Now, how are we getting these answers? I'm pretty much picking, or not so much picking, I'm just going straight into here. But how am I getting -3 and 1? So that skip word, that extra steps that we can take to find those values instead of jumping straight into it, is that I take the factor x plus 3 and I set that equal to 0. So then from here, isolate x by getting rid of the 3. Opposite of plus 3 is -3 on both sides. This cancels. You're left with x equals -3. Take the second factor. X minus 1 is equal to 0. You add 1 to both sides. This cancels. X equals to 1. So keep in mind, it's not just down to 2 factors. You might have 3, 4, 5 factors, and you're going to have to do this. Now, what happens if I just have x? So remember dealing with that x here. Remember, x represented 0. So if I take this factor, x, and I set it equal to 0, do you see how it's already solved? Oops, equals -3, and then this one as well. So that's what we're doing. The thing is, from going from this step that we're doing right here goes right in between here, right between the black and the black writing and the white writing here. This whole step, we can kind of easily jump straight into this if they're formatted just like that: x and then whatever number, plus or minus whatever number. But again, these are the solutions to the polynomial. Let's go ahead and take a look at this one on slide 16. So what we're going to go ahead and do is says find the solution to this polynomial. I can tell you already there is one thing in you're going to be able to set them equal to 0. Now, this 3 that's sitting outside does not really do anything for me. And I can even show you algebraically how we can make that disappear. So we have 3x minus 2 parentheses x squared minus 9. Now, this x squared minus 9 can be factored out even more. That's the difference of squares. You have the minus, you can take the square root of each one for a and b and determine that. But all of this is being multiplied. So if I want to get rid of this 3 that's trying to get multiplied, I do the opposite of it. I divide both sides by 3. And here, this will cancel. I'm left with x minus 2. And what I'm going to do is I'm going to factor out x squared minus 9 for you. X squared minus 9 is the same thing as x plus 3, x minus 3. Or vice versa, minus 3 plus 3. Then you have x plus 7. And here, 0 divided by 3 is still 0. Now go ahead and list me the solutions or the zeros that quick trick that we found, like x negative 2, that should be your positive 2, right? Opposite side. Go ahead and continue that and make sure you select. You should have selected 1, 2, 3, 4. 4 factors, 4 solutions there. So go ahead and enter that for slide 16. So moving on to slide 17 here. So solutions or zeros of the polynomial function correspond to the x-intercept of the graph of the function. So we can identify the x-intercepts of a function by finding the zeros. Remember, all those words wrap up to one another. So it says, first find the factors of the function as shown. So here we start out with p of x, which is x squared minus 7x plus 12 times x minus 1. I like the x minus 1, it's already factored, but this x squared minus 7x plus 12, I have 3 terms. I can use a giant X on there. They already factored it for us, but again, I just want to make sure we see those numbers where they're coming from. So we take our a and c, multiply it. Our a value is 1, our c is 12. 1 times 12 is 12. The bottom number is down here is our b, which is negative 7. What 2 values multiply to get 12 and add to get 7? So we write out the multiples of 12. 1 and 12, 2 and 6, 3 and 4. After the 3 is going back to 4, so we won't rewrite the repeat. So it's which pair can give me 7. 3 and 4 give me a clear 7. So I'm going to add 3 and 4. Now, if I multiply 3 times 4, I get positive 12. But if I add them, I get positive 7. I need negative 7. So they both need to carry my negative, and we'll double check to see if that's true. Negative 3 times negative 4 is positive 12. Negative 3 minus 4 is negative 7. So that's why they have it listed. X minus 3, x minus 4, x minus 1. So to find the solutions, remember, we can separate each factor. X minus 3 is equal to 0. Right here, it's not equal to 0, but we say, okay, because we're looking for our x-intercepts, remember, p of x is another way of saying y. To find x-intercepts, you set your y is equal to 0. So you separate each factor and you solve for x independently and you get that x. Or you can jump into the little shortcut that we know. Because I have the value of minus 3 here, x is going to equal to the opposite of negative 3, which is positive 3. Negative 4, that means that's 4. Negative 1, positive 1. And they're going to come up with the same results. So there on the graph, they actually graphed it for you. Here, there's your results. There's your 1, there's your 3, and there's your 4. So they provided the graph. Then use the zero product property to find the zeros and therefore x-intercepts of the function. So the zero product property is this piece over here. Taking your factors and setting them equal to 0 and solving. But you know the shortcut to this. Let's go ahead and take a look at slide 18. So the fundamental theorems of algebra states that any polynomial function of a degree of n has n amount of zeros. For example, the function f of x, x to the fourth minus 3x cubed plus 2 has 4 zeros because it has a degree of 4. So remember, whatever degree number it has, it's gonna have that's the highest degree, that's gonna be the same amount of zeros or solutions you have. So it says examine the graph of f. So what they did is that x to the fourth power minus 3x cubed plus 2 is graphed for us on the left-hand side. If you take a look at it, does it touch your x-axis 4 times? If you're counting, it should count 2. So it doesn't match what happened there. So it says examine the graph of f. Notice that the graph touches the x-axis only 2 times, which means it only has 2 real solutions. Therefore, two of the functions 4 zeros are complex. So we have 2 real solutions, and then there must be 2 complex there. The degree of the polynomial reveals how many solutions there are. We need to examine the graph, factor, and divide out factors to determine whether the solutions are real or complex. So here we do have real solutions, and they're actually telling us that, remember, you can't have one or the other. You have to have, you can't have real and complex. You can only have, or actually whatever amount of degree it matches up to, the rest would be considered complex. And there's mainly only, remember, the complex situation is that you can have the complex number and its conjugate. So like if the complex number is 3 minus 2i, the conjugate of that is 3 plus 2i, always leaving you with 2 complex. So let's take a look at this one. The graph, so this is slide 19. If the graph of the 5th degree polynomial function to determine the number of real complex zeros the function has. So they're telling us that this is to the 5th degree. So we know we have a degree of 5. How many times are we touching how many real zeros are there? In other words, count how many times is it touching the x-axis? Whatever number you get, the complex is going to match up to the 5. So we count off 1, 2, 3. We have 3 real zeros, but remember, we need to have 5 solutions. So then we must have 2 complex. So now we're in the case where we can have real solutions and complex solutions at the same time. So what I'm going to go ahead and do is save slide 20 for part 2 of this video. So then we can end this one here, because we're going to go ahead and talk about the multiplicity, which is another concept to take a look at.